The particle model of matter. 2.1 Describing matter. Criminals will continue to shoot, stab, and strike police officers because these actions come from their fallen, evil heart. Scientific knowledge can't do anything about the heart, but by using scientific knowledge, we can try to protect those who go into harm's way to protect us. Placing some kind of material barrier between a weapon and a person could protect him from an assault and save his life. What properties does matter have that can use for such an important purpose? Operational science relies on observation, so let's do some observing. Look around the room. What do you see? There are probably things made of wood, metal, fiber, plastic, and many other solids. Tear may be a glass or bottle containing a liquid beverage. If you blow on your hand, you can feel the air moving across your skin even though you can't see it. What are all these different kinds of physical materials made of? That would be matter. All substances in the universe are forms of matter. Carefully look around you again. Using all your senses, note those things that don't seem to be physical substances. What about the light shining through a window? What is the signal that a TV turns into images and sound? How about the warmth given off by a light bulb? While you can sense these things directly or indirectly, they aren't matter. So what is matter? People have long defined matter as anything that takes up space and has mass. But this statement isn't a definition, it's a description. Matter, like many other things that scientists study, can't be defined using more basic ideas. Matter can exist as immense objects, such as a supergiant star 500 times the size of our sun. Or it can exist as extremely small objects, such as atoms or subatomic particles. As you will learn, all matter is made of these tiniest of particles. Try to group the forms of matter that you see in the room into a few main categories. Most of the visible matter is solid. The beverage in a glass is a liquid. The air you are breathing is a gas. These kinds of matter are probably familiar to you. If there is a fluorescent light in the room, a plasma exists inside the lamp. This is a less familiar but very common form of matter in the universe. Matter occurs in these different states because of the arrangement and motion of its particles. 2.2 The particle model. About 400 years before Christ, Greek philosophers debated about the nature of matter. Several of these men believed that all matter was continuous. That is, it could be subdivided repeatedly into infinitely small particles. Other philosophers were convinced that matter wasn't continuous. After subdividing a substance enough, you would eventually reach a particle that couldn't be divided further. The philosophers called these basic particles atoma, meaning indivisible, and those who held to this idea were called atomists. Remember, these people had no knowledge of atoms or molecules, so these ideas about material things that couldn't be seen were pretty amazing. The debate in ancient times ended when the teachings of the influential Greek philosopher Aristotle, who opposed the atomists, eventually won out over his rivals. He objected to atomism because it required a void or vacuum to exist between atoms, something Aristotle rejected on philosophical grounds. How could nothing exist? Instead of atoms, Aristotle saw matter as continuous and full of the potential to become anything. When matter takes on form, it becomes the objects that we see. Aristotle's writings about nature influenced the models of European science for nearly 2,000 years, including a large part of the Christian era. Sadly, Christian acceptance of Aristotle's ideas came about because church teachers tried to combine Greek and Christian worldviews together, even though they were largely incompatible. During the Renaissance, European scholars studied ancient literature and poetry from Greek and Roman times. Even though most of the original atomistic writings had been lost, the writings of Aristotle survived, including his critiques of atomist philosophies. As early as the 1300s, European scholars were aware of a form of atomism, but a useful particle theory of matter didn't gain a foothold in European science until the 1600s. See the facet on the facing page. Scientists generally accepted the model by the mid-19th century, but not until the 20th century did scientists understand how small and complex the particles of matter are. Physicists measure the diameter of a typical particle of matter in nanometers. The nanometer is the metric unit used for measuring such small lengths. If you could lay 1 million particles of water side by side, their combined lengths would be equal to the thickness of a page of this textbook. There are different kinds of particles of matter, but the most common particle that scientists refer to is the atom. Atoms are the building blocks of matter. They can combine to form larger particles or masses of atoms. Can we observe anything so small? A microscope known as the Scanning Tunneling Electron Microscope, STM, allows scientists to detect atoms on the surface of specially prepared materials. The May-chine does not see atoms directly. Instead, it detects the electrical influences surrounding the atoms and converts them into artificial images that represent the atoms. See Figure 2.5. Even before the STM, however, physicists had gathered enough indirect evidence to convince them that atoms do. 2.3 Evidence for the particle model. A good scientific model explains all laboratory observations. If the particle model of matter is workable, then it should be able to explain how matter behaves in everyday situations. The particle model of matter assumes two important things about matter. It is made up of tiny particles, atoms or molecules, and the particles are in constant motion. The way sugar dissolves in water, so that every part of a sugary drink is sweetened, agrees with this model. You may have noticed how quickly a perfume or the smell of ammonia can spread through the air in a room. A crystal of a colored chemical compound, see Figure 2.6, that disperses into a beaker of water, even without stirring, supports the particle model. Particles of the compound break away from the crystal and slowly move off into the water. Eventually, the water is evenly colored. The dispersion of a substance through another by particle motion is called diffusion. These examples seem to support the particle model, but they support the continuous model of matter as well. Remember that Aristotle believed that matter could be subdivided indefinitely, so taste, smell, or color should easily diffuse throughout liquids or gases. We need to look further for stronger evidence of particles in matter. Chemists discovered the first indirect evidence for particles of matter in the late 1700s. They noticed that when they weighed certain chemicals and then burned them in air, the weight of their residue after burning was different from the weight before. The ratios of the before and after weights were often small whole numbers like 1.2 or 3.5. Other kinds of chemical changes produced similar ratios. Chemists began to suspect that they were observing the evidence of individual particles chemically combining in definite ratios. Scientists first recognized the direct effects of particles of matter in motion in 1827. Robert Brown, an English botanist, was examining the interior of tiny plant spores with a light microscope. He saw cellular parts within the spores jostle back and forth, as if something were striking them repeatedly from different sides. Yet nothing was touching them except the cellular fluid in which they were floating. Although other scientists had observed this motion before him, he was the first to report his findings in a widely read paper. Others after Brown suggested that the jiggling motion of the cell parts was due to the impacts of fluid particles striking them randomly from different directions. Today, we call this movement of bits of matter in liquids and gases Brownian motion in his honor. These are only a few of the evidences that have led scientists to conclude that tiny particles in random, constant motion make up all matter. This fundamental model of matter is often called the kinetic molecular theory of matter. 2.4 The atom. Matter that we can detect with our senses is made of atoms, molecules, or large structures of one or the other. The atom is probably the most familiar to you. It's the basic particle that makes up all matter. Atoms contain protons, electrons, and usually neutrons. These subatomic particles exist within a tiny spherical region in space that is the atom. At the center of the atom is the nucleus. The nucleus contains one or more protons. The number of protons in the nucleus determines the kind of atom. Each proton carries a single positive charge. The nuclei of most atoms also contain neutrons. These particles have about the same mass as a proton, but they have no electrical charge. They are neutral. Electrons are strange things that can exist in the spherical volume of space around the nucleus, or as tiny particles flying between atoms. Each electron carries a single negative electrical charge. The electron's mass is only a tiny fraction of a proton's or neutron's mass. The electron cloud that surrounds the nucleus determines the size of the atom. In an ideal atom, the numbers of electrons and protons are equal. So the number of positive charges in the nucleus equals the number of negative charges in the space around the nucleus. The opposite electrical charges cancel each other, so we say that an ideal atom is neutral. 2.5. The molecule. A molecule is a distinct particle formed when two or more atoms bond together and become separate from other atoms. A molecule can be very simple, like an atmospheric oxygen molecule, which is made of two identical oxygen atoms. Molecules can also be very large and complex, containing hundreds of millions of atoms, like DNA. Physicists usually treat individual molecules as if they were BB-like particles, since the details of what they are made of aren't as important as how they move and affect other particles. Chemists, though, are more concerned with the kinds and arrangements of the individual atoms in a molecule, and how they determine the molecule's properties. Molecules are made of atoms, so they also contain the protons and electrons that form their atoms. The number of protons within an ideal molecule equals the number of electrons in the molecule, so it is also electrically neutral. 2.6 ions. Under certain conditions, atoms and molecules can gain or lose electrons. If they have more or fewer electrons than protons, then there is an electrical charge imbalance. Particles with unbalanced electrical charges are called ions. Anions have more electrons than protons and have a negative electrical charge. The opposite condition results in cations, which have a positive charge. Ions form important and common forms of matter like rocks and salts. Electric fields can also attract and repel ions. Later in this course, you will see how atoms, molecules, and ions build the matter from which the universe is made.